Okay, so for FRK number 4, we have a nonlinear spring, and we are given a data table that shows the various distance x that the spring is compressed, along with the corresponding force that is required to compress the spring that certain amount of distance, F. Now, we are also told that the magnitude of the force applied by the spring is in the form of f of x is equal to ax squared. So this essentially gives us the relationship between the force applied and the distance compressed. Now part A tells us or asks us to determine which quantities should be graphed in order to yield a straight line whose slope could be used to calculate the numerical value for A. Okay, so usually a straight line has the form y is equal to mx, right? I'm gonna ignore the b because b doesn't really matter in this case. Okay, so matching this with this equation, it looks like for our y-axis, we're gonna graph f, and if a is our slope, m, that means our x-axis will be x squared then. So I guess the values we need to graph is force for our y and x squared for our x. And that's the answer to part A. Now part B. Part B says to calculate for any quantities identified in part A that are not given in the data and record these values in the data table above, or make your own chart, I guess. Okay. So I'm gonna recreate the data table. So let's see, x of m, f of n, and then there's a missing thing right here. Okay, so this zero. So here's what it looks like. I'm gonna basically copy it now. 0.05, 0.10, 0.15, 0.20, and 0.25 for 17, 38, 68, and 106. Okay, so in part A, I said that we need to graph f and x squared. We already have f. Wait, this is Newton's, by the way. We already have f. Now we need x squared, so x squared. Squaring x, that means our units is going to be m squared then. So square of this number is 0.0025. Square of this number is 0.01. Square of this number is 0.0225. Square of this number is 0.04. And square of this number is 0.0625. Alright, so that is our missing value, and we filled our chart. Alright, now part C wants us to use the grid below or generate your own and plot the quantities you indicate in part A, and label the axis and variables appropriate and to indicate the scale. Okay, so I'm going to create my own graph. So let's see, 100, since it goes up to 100, so it's right there, 100, then 80, 60, 40, 20, and so this leaves 0 right here. So this axis is force, and then this axis will be x squared, and then now I'm gonna scale it. So I have 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, and last one is 0.07. Alright, so now time for the graphing. So first set of data, 0.0025 and 4. So 4 is, so this is 10, and then half of that should be somewhere around 4. This is barely 0, this is 1/4 of 0.01, so it should be somewhere right here and right here. So first point's right there. Second point, 0.01, so exactly right here. And 17 should be somewhere underneath 20, so right here. Next point, 0.0225, so 1/4 of the way between 0.02 and 0.03. And 38 is just below 40, so right here. Next point is 0.04, so here. And then 68, that's, so right here should be 70, and then below that a little bit, so 68. And last point, 0.0625, so 1/4 the way between 0.06 and 0.07, so right here. And 106, so right above 100, right here. All right, and then best straight line. Sorry, I don't mean to connect this, but something like that. This should be a little bit below. Basically, it's not directly on the line, but I kind of drew it that way. Okay, there. All right. Now part D says use the graph to calculate A. So essentially A is the slope, and that's slope is rise over run. And so I can pick any 2 points on this graph to help me find A. So I'm gonna use this point right here and the beginning point, which is 0, 0, obviously. So it's gonna be 106 minus 0 newtons over 0.0625, I believe is this point, 0.0625. That's meter squared minus 0 meter squared right here. And that gets me 1696. Oops, 1696. And that's my A. So this is my spring constant. All right. Now part E. So it says, so we have a new scenario. The spring is placed horizontally on the floor. One end of the string is fixed onto the wall. A cart of mass 0.5 moves on the floor with negligible friction and collides head-on with the free end of the spring and compresses it a maximum distance of 0.1 meter. Now it says to calculate the work done by the cart in compressing the spring 0.1 meter from its equilibrium length. Okay, so work. Now the equation for work is the integral. So if you integrate f of x with respect to distance, you get work. So I'm gonna integrate f of x from 0 meter to 0.1 meter because that's how much is compressed and this is uncompressed. And so, and I know what f of x is. F of x is 169.6 x squared. because all I have to do is plug in this coefficient to the original equation, which is f of x is equal to ax squared. So this is my a now. Alright, so what I have is work is equal to the integral from 0 to 0.1 1696 x squared dx. So if I integrate this, I would add 1 to the exponent, giving me, so it's constant stays the same, add 1 to the exponent, giving me x to the power 3, then divide by the exponent, so divide by 3. And then I can't forget my bounds, so from 0 to 0.1. So I'm going to plug 0.1 and 0 in. So 169.6, 0.1 for x, 3. And if I plug in 0, this whole term is going to be 0, so I don't have to plug in at all. So this is basically what this is equal to. And then plug that into the calculator, I get 0.565 joules. So that is how much work is done compressing the spring. Okay. Now part F. Part F tells me to calculate the speed of the cart just before it strikes the spring. Okay, so to do this, I know that work is equal to the change in kinetic energy, and I know that kinetic energy has speed in it, so that will help me find my speed. Okay, so F, part F, work is equal to change in kinetic energy, and the change in kinetic energy is KEF minus KEI. I know that KEF is 0 because the spring stops moving, or the cart stops moving. So work is going to be equal to -1/2 mVi squared. So Vi is basically the speed of the cart just before it strikes the spring, which is what we're trying to find. Now, this work is a little bit different from this work right here. This work is exactly the opposite of this work, so basically -0.56, because the work in part E, as a reminder, is the work done by the cart in compressing the spring. But this work right here is the work done by the spring onto the cart. So this work is exactly opposite. So this is why it's going to be negative. So I'm going to plug in my numbers. This is -5.65 joules. Negative this number is equal to -1/2. Mass is 0.5 kilograms, the cart. And then Vi squared is what we're trying to find. So if I isolate for Vi, I'm going to have to multiply -2 over here and then divide by 0.5 and then square root everything. So here's what it's going to look like. So -0.565 times -2 divided by 0.5 and then square root everything. Plug this into the calculator, I get 1.504 meters per second for my Vi. Vi is basically the speed of the cart just before the cart strikes the spring. So this is it, my answer.